Hello! Today we're going to be talking about roots and zeros of polynomial functions. So our objectives for today are that students will be able to determine the number of roots for a polynomial equation and find the zeros of a polynomial function. Let's get started. Alright, when we're talking about types of roots or synthetic types of roots of a polynomial function, we're saying that these following statements are equivalent for any polynomial function. So we can say that C is a zero. Oops, hold on, meant to get my highlighter. We can say C is a zero of the polynomial function. We can say C is a root or a solution of the polynomial equation f of x equals 0. We can say x minus C is a factor. All right, so here we're talking about x minus C. And if C is real, then C, comma 0 is an intercept of the graph of f of x. So that becomes our x-intercept. So I don't know if you guys remember at the beginning of the year, we talked a lot about a vocabulary. And anytime we're talking about roots, zeros, solutions, x-intercepts, it's all the same thing. These are all just different names for the same thing. And there's different forms it can come in, as you can see. So C could be a 0, C is a root or solution of the polynomial equation, could be a factor, could be an intercept of the graph. It's all the places where your graph crosses the x-axis. Those are all roots or solutions to our polynomial functions. So today we're going to be talking about the fundamental theorem of algebra. And the fundamental theorem of algebra states that every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. So if it's a polynomial equation, if it has an x, it has at least one root that's either real or imaginary. The corollary to the fundamental theorem of algebra is that a polynomial equation in the form p of x equals 0 of some degree n, with complex coefficients has exactly that many or n roots in the set of complex numbers, including repeated roots. Alright, so now let's see a couple examples of what this actually means. Right now it's just a bunch of words, a bunch of mumbo jumbo, so let's see what this actually means. Alright, so here's an example where we want to solve the equation 6x to the third plus 3x equals 0, and we want to state the number and type of roots. So based off of the fundamental theorem of algebra, we know that because it's an x to the third power, that it has to have 3 roots. We don't know if they're real, we don't know if they're imaginary, but there has to be 3 roots. Oops, meant to get the pen. So it has 3 roots total. Now, we want to find these roots or to solve the equation. So what we would need to do is take our equation, 6x to the third plus 3x equals 0, and we want to solve for x. So we want to use one of the many methods we've learned, factoring, in order to solve for x. So the first thing we want to do is take out that GCF. We know that it has 3x in common. If we factor out a 3x, we're left with 2x squared plus 1 equals 0. Then set each of these equal to 0 to solve for x. So take 3x, set it equal to 0, divide by 3, we get that x equals 0. Then we're going to want to take 2x squared plus 1, set that equal to 0, subtract 1 from both sides, divide by 2, x squared equals negative 1/2. Let me get some more space here. All right, then take the square root of both sides, and we get that x equals square root of negative 1 over square root of 2. Now we know square root of negative 1 gives us plus or minus I. And we can't have square roots in the bottom, so we need to multiply the top and the bottom by rad 2. Then I still need more space here. So multiply the top and the bottom by rad 2, and we get plus or minus I rad 2 on top over 2 on the bottom. And this is our part of our solution. So here we have one root. Here we have two roots because it's positive this and negative this because it's plus or minus. So we have three roots. We have 1, 2, 3. One of them's real, two are imaginary or complex because this one has an I in it. So we would say that we have one real. So first of all, list your solutions as a solution set. X equals 0 and plus or minus I rad 2 over 2. And we have one real root and two imaginary roots. And that's how we would state the number and types of roots. And we're done. All right, so number 1 in our exercises, we want to solve this equation, so find our roots, state the number and type of roots. So based on the fundamental theorem of algebra, we know we're going to have two roots because it's in x to the squared. We got it's to the second power. That means there's two roots. That's what the fundamental theorem of algebra tells us. Now we want to solve for x, so we would need to factor out our quadratic equation here in order to find the number of roots, or in order to find the roots. We know that there's two roots. We want to know what are they, and are they real or imaginary? So first thing, we look at this, we say, let's try to factor it. Two numbers that multiply to negative 21 add up to 4. Our answer would be 7 and negative 3. So we can factor this, and we get x plus 7 times x minus 3 equals 0. Then set each of these equal to 0. So x plus 7 equals 0. Subtract 7 from both sides. X equals negative 7. And then set x minus 3 equal to 0. Add 3 to both sides. X equals 3. So let's write our final answer as a solution set. So let's get some more space here. So we would say x equals negative 7 and positive 3. And this is two real roots. So the only time it's complex or imaginary is if we have an I involved. Here it's just two whole numbers, two real numbers. So we have two real roots, and they are negative 7 and positive 3. All right, number 3. So we still want to solve the equation, state the number and type of roots. We see that it's an x to the third power, so we know we're going to have 3 roots total. We just need to find out if they're real or imaginary. So first things first, we want to factor out the GCF. So the GCF here would be 4x, because that's what they have in common. We're left with 3x squared plus 25 equals 0. Then we want to set each of these equal to 0. So 4x equals 0, divide by 4, x equals 0. There's one of our roots. Then we want to set 3x squared plus 25 equal to 0. And this one's going to be a little more complicated. All right, so subtract 25 from both sides. We're left with 3x squared equals negative 25. Divide by 3. X squared equals negative 25 over 3. Take the square root of both sides. So we want to rewrite this as x equals plus or minus the square root of negative 25 over the square root of 3. Now we can rewrite this as plus or minus 5i on top, and we're still left with the rad 3 on the bottom. But as you remember, we can't have radicals, we can't have square roots in the denominator. So in order to get rid of that square root in the denominator, multiply the top and the bottom by rad 3. We multiply it by the same thing, because then we're going to be left with plus or minus 5i rad 3 on top. Rad 3 times rad 3 gives us rad 9. Rad 9, square root of 9 is 3. And this would be our other solution. So, and there's two solutions because we have positive this and negative this because it's plus or minus. So if we were to write our answer, we would write our final answer as solution set x equals 0 and plus or minus 5i rad 3 over 3. And here we have one real, which is 0, one real root, and two imaginary or complex roots, because these two solutions right here have an I. And that would be our final answer. All right, the other thing we're going to be talking about today is the complex conjugate theorem. So the complex conjugate theorem states that if we were to suppose that a and b are real numbers, where b is not 0, and if a plus bi is a 0 of the polynomial function and it has real coefficients, then the complex conjugate a minus bi is also a 0 of the function. So let's see an example of how this works. All right, here's our example. We want to find all the zeros of this polynomial function. First of all, since the function has a degree 4, it's a fourth degree polynomial, we know that the function has 4 zeros. We know this by the fundamental theorem of algebra. Then we take our function and we want to first use synthetic substitution to test some possible zeros. So in order to test some possible zeros, we want to first start with the most basic zeros, 1, 2, 3, 4, and so on, right? Start with your basics. And it's pretty much just a game of guess and check right now. So start with 1 and do synthetic substitution and see if 1 is a 0. If we get a remainder of 0, then we know 1 is a 0 of the function. So we list out all of our coefficients, 1, negative 15, 38. Oh, oops, can't forget that 0 in there. Hold on. We skipped over an x to the third, so we have to put a placeholder 0, negative 15, positive 38, negative 60. So we're going to bring down that 1, 1, 1, 1, negative 14, negative 14, 22, 22, and let's see, we get negative 38. That is not 0. Our remainder needs to be 0, so we know that 1 is not a solution. 1 is not a 0 of the function. All right, so let's test out another 0. Let's try 2. 2. Same coefficients on the inside of our box, 0, 1, 0, negative 15, 38, negative 60. Bring down the 1, we get 2, 2, 4, negative 11, negative 22. Let's see, we get 16, then 30, oh, not 38, 32, and we get negative 28. This is not a solution because we need to get 0 here. So 2 is not a solution. Let's try another one. Let's try 3. 3. 0, negative 15, 38, negative 60. Bring down the first term. 3, 9. And then negative 18, we get 20, 60, and oh, we get 0 as our remainder. We found a 0. So 3 is a 0 of the function. All right, so we know that 3 is a 0 of the polynomial function that we're working with. Now we want to take the coefficients that were left over. So when we did synthetic substitution and we had 3, we were left over with the digits or the coefficients 1, 3, negative 6, 20, and we got 0 as our remainder. All right, so now we want to take these coefficients and try synthetic substitution again to find another 0 of the polynomial function. All right, so take our coefficients and we can forget about the 0. Try another number. It's a game of guess and check. So let's try, how about Let's try -2. All right, because we already tried 1, 2, and 3. How about -2? Bring down a 1, -2, 1, -2, -8, +16, and we're left with 4. That is not 0, so -2 is not a 0 of what's left of our polynomial. Now let's try -5. We still have to use these numbers right here inside, so 1, 3, -6, and 20. Bring down our first term. We're left with -2, -10, or wait, sorry, that should be a +10. -5 times -2 gives us +10. We're left with 4, -20, and 0. And look at that, we found another solution. We know that -5 is another 0 of our polynomial function. All right, so -5 is another 0. Now we want to take what was left over after we did synthetic substitution with -5. We were left with 1, -2, 4, and 0. And we want to write another polynomial based on those coefficients. So we would get this right here. We would get x squared minus 2x plus 4. Now in order to find the other zeros, now that we have a quadratic, we can factor it, and that's a lot easier than having to use synthetic substitution. All right, so we try to factor it. We want two numbers that add up to 4, multiply out to 4, add up to -2. And if you think about it, there's actually nothing that works for that. So we want to use another method for factoring quadratics. And honestly, the easiest thing to do would just be to do the quadratic formula. So first try to factor, and if you can't factor, just go straight to the quadratic formula. So let's say x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. X equals +2 plus or minus the square root of 4 minus 16 all over 2. Let's move this up so we've got some more space. X equals 2 plus or minus the square root of -12 all over 2. If we will try to break down square root of -12, we get square root of -4 and 3. We can change this to plus or minus 2i. So we're left with 2 plus or minus 2i rad 3 all over 2. And we can divide all of these by 2. Right, so we're left with 1. And our solution will give us 1 plus or minus I rad 3 all over 1, or we don't have to write the all over 1. And that's our solution. All right, so those would be our remaining zeros. All right, therefore, we have concluded that the function has two real zeros at 3 and -5, and two imaginary zeros at 1 plus or minus I rad 3. So write our solution as a solution set: 3, -5, and 1 plus or minus I rad 3. 2 real and 2 imaginary. And you're done. All right, so let's do another example together. We want to find all the zeros of each function. So we're going to start with this function right here. Number 1, we've got f of x equals x to the third plus x squared plus 9x plus 9. So we want to start by doing our game of guess and check and seeing if we can find a zero of this function. So we're going to start with synthetic substitution. Let's try out 1. All right, put our coefficients in there. Bring down the first term. 1 times 1 gives us 1. We've got 2, 11, 20. That does not work. We need a 0 here. So now let's try, how about -1? All right, because you can try any number. I recommend you start with 1, 2, 3, negative 1, negative 2, negative 3. All right, we use the same coefficients that are inside our first box. Bring down the first term. 0, 0, 9, negative 9, 0, and you're good. We found one of the zeros of our function, so one of the zeros is negative 1. Then we take what's left. We take this right here and write a depressed polynomial. So we would say x squared plus 0x plus 9. That is our remaining polynomial, and it's in the quadratic form. So set it equal to 0. Subtract 9 from both sides. X squared equals negative 9. Take the square root of both sides, and you get x equals plus or minus 3i. So the solution to problem number 1 would be x equals, the first root we found was negative 1, and plus or minus 3i. And we have one real and two imaginary solutions or roots. And that's our final answer. All right, problem number 3. Same thing, we start by doing our guess and check synthetic substitution. So let's start with 1. Put our coefficients inside of our box. So 1, negative 10, 34, and negative 40. Bring down the first term. Negative 9, negative 9. We're left with 25, 25, negative 15. Doesn't work because we need a 0 here. All right, let's try. All right, I'm going to give you guys a little hint. Let's try 4. All right, so yes, I know that I somehow know which zeros to try right off the bat. It's because I've done this problem before. There's no real way of knowing what's going to work. You just have to sit there and guess and check until you find one. So yes, it could be a little painful at times if you can't find one, but keep guessing and checking until you find one of those solutions. So I'm going to help you guys out, and we're going to try 4 now. 1, negative 10, 34, negative 40. Bring down that first term. Negative 24 gives us 10. 40, we get 0. And look at that, we've got a solution because our remainder is 0. We know that 4 is a 0 of this function. It is a solution. Then we want to take what's left here and write a depressed polynomial. So write our quadratic that's left. We get x squared minus 6x plus 10 equals 0. And right off the bat, if we do our diamond and try to factor this, we're going to see that there isn't two numbers that multiply to 10 and add up to negative 6. So we're going to skip ahead and go straight to the quadratic formula. So we're going to say, let me get my pen, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. X equals positive 6 plus or minus the square root of 36 minus 40 all over 2. And I'm just going to go up top because I'm running out of space here. X equals 6 plus or minus the square root of negative 4 all over 2. Square root of negative 4 we can rewrite as 2i over 2. Then we want to divide each of these by 2. So 6 divided by 2 and 2i divided by 2. It's going to give us 3 plus or minus I. And there's 2 more roots or zeros. So then our final answer we would want to write as, let's see, x equals our first 0 up here we found was 4. We found using synthetic substitution, and our other 2 zeros are 3 plus or minus I. So we've got 1 real and 2 imaginary. And that's our solution. All right, for number 5, what I want you to do is pause the video. When I say go, I want you to pause the video and try to do number 5 on your own. So first do synthetic substitution to find one of the zeros, and then take your remaining quadratic, factor it, or use the quadratic formula to find your other zeros, because we know we're going to have a total of 3. All right, so pause your video now and try to do number 5. When you come back, the answer will be written on the screen for you, and we'll go through it. So pause your video now. All right, if you're feeling stuck, what I want you to do is try doing -2 using synthetic substitution. I'll give you a hint. -2 is one of your zeros, and make sure your synthetic substitution is set up like this. Don't forget that placeholder 0. All right, so pause your video again and try to do it from here. All right, so you should have done synthetic substitution with -2 on the outside as one of your zeros. You're left with coefficients 1, -2, 10, and you got a remainder of 0, so you know that this is in fact a zero of the function. Your remaining quadratic is x squared minus 2x plus 10, set it equal to 0. Do the quadratic formula to solve for x. So we plug in -b plus or minus the square root of b squared minus 4ac all over 2a. We simplify, we end up with x equals 2 plus or minus 6i rad 2. Divide both terms in the numerator by 2. You end up with x equals 1 plus or minus 3i. Now, because you got a remainder of 0 here, we know -2 is one of our solutions, one of our roots, and 1 plus or minus 3i are our other two roots, and they're both imaginary. So we have one real root, or 0, two imaginary zeros. And that is our solution. All right, so I hope you learned a thing or two about roots and zeros today, and about the fundamental theorem of algebra, and about the complex conjugate theorem. And so now please look to the board or look to your teacher to see what to do next, and I hope that you have a great day.